Hello viewers, in the previous series of gaseous state, we have discussed the collision properties of gaseous molecules like collision diameter, it is represented by sigma and sigma is equal to r. Then collision frequency, it is represented by Z. For bimolecular collision, it is Z11 is equal 1 by root 2 pi sigma square C average into n square. After that, we discussed free mean path. It is represented by lambda and lambda is equal 1 by root 2 pi sigma square into n. Now, in this lecture series of gaseous state, we will discuss the liquefaction of gas, then the methods of liquefactions. After that, we will also discuss the application of gas laws in daily life. As viewers, you know there are three states of matter: solid, liquid and gas. Let's discuss some kinds of phase transition. Like solid phase changes to liquid, this phase transition is known as melting. Example is melting of ice. Another phase transition is sublimation. Sublimation is conversion of solid phase to gas. Very good example is sublimation of dry ice. Now, another phase transition is when liquid state changes to solid state. This type of phase transition is known as freezing. Example is freezing of water or liquid metal. Now, vaporization. Vaporization is conversion of liquid phase to gas, like evaporation of water or refrigerant. One more phase transition, when gaseous phase changes to liquid, this type of phase transition is known as liquefaction. Its very good example is formation of dew. One more phase transition, that is deposition. Deposition is conversion of gaseous phase to solid is deposition. Very good example of this phase transition is formation of snow and frost. So, let us start with liquefaction of gases. Liquefaction is a process, as I told you before, that liquid phase changes to gases. So, liquefaction is a process in which a gas changes into liquid state, and it is very important for scientific, industrial and commercial purpose. So, gases can be liquefied by lowering the temperature, that is by cooling. We can convert gaseous phase into liquid state. Second, we can increase the pressure, that is known as compressing. So, what happens under high pressure and at low temperature, the kinetic energy of the gas molecules decreases. So, as a result, the molecules come close to each other and ultimately the gas changes into liquid state. Compress the gas at temperature less than its critical temperature. By this process, we can convert gaseous phase to liquid phase like this. These are gaseous molecules at low temperature and high pressure. These molecules come closer due to kinetic energy there decreases. So, due to decrease in kinetic energy, these gas molecules come together and this is known as conversion of gaseous phase to liquid phase. But some gases like carbon dioxide, helium, hydrogen, nitrogen and oxygen, these can't be liquefied by the application of pressure only. Andrews in 1863 demonstrated that for each gas there is a certain range of temperature, that is known as critical temperature. It is a temperature above which it is impossible to liquefy the gas, howsoever pressure is applied. For liquefaction, each gas must be at or below its critical temperature. Here is a figure for you. This figure is for isotherm of carbon dioxide. Let us check. Critical temperature of carbon dioxide is 31.1 degree centigrade. So, it is impossible to liquefy the carbon dioxide gas above 31 degree centigrade, no matter how high the pressure is applied. And below this 31.1 degree centigrade temperature, the carbon dioxide can be liquefied into supercritical fluids, while above 31.1 degree centigrade, it remains in gaseous state. We have discussed in it previous lectures. Let us discuss how can we liquefy the gas. We can liquefy gas as if we make gas to work against its own internal forces by causing it to lose energy, and they will easily liquefy. Second, if we make the gas to do work against an external force causing the gas to lose energy, and easily gas will liquefy. So, there is liquefaction temperature for some gases here. N-butane liquefies at minus 0.5 degree centigrade, propane liquefy at minus 42 degree centigrade. The liquefaction temperature for ethane is minus 88 degree centigrade, and for methane it is minus 161 degree centigrade. For air, the liquefaction temperature is minus 195 degree centigrade, while for hydrogen gas it is minus 253 degree centigrade. Now, let us discuss the application of liquefaction. The liquefied carbon dioxide gas is used as soda fountains, while liquefied oxygen is used in hospitals for patients suffering from breathing problems, while liquefied chlorine is used as a good disinfectant and bleaching action. Liquefied nitrogen gas is also used as a refrigerant, and liquefied hydrogen is used as a rocket fuel. There is very good example of liquefied gas, it is liquid natural gas. Let us discuss its advantage. Natural gas is cooled until it liquefies at minus 160 degree centigrade, and it changes into LNG. So, LNG is a colorless, odorless and non-toxic gas. The volume of natural gas reduces to 600 times. So, finally, it is safe to transport and store. A very good advantage of LNG is environmental advantage. By LNG, there is no production of ash, no sludge production, no hazardous waste is produced. The particulate emission are approximately 95% less than burning coal. Now, let us discuss the methods of liquefaction of gas. Gases can be liquefied by cooling and by using Joule-Thomson effect. Let us discuss the methods of liquefaction of gases by cooling. So, by using the freezing mixture, we can liquefy gas. A simple method for producing lower temperature than ice is to add various salt to ice. So, addition of these salts to ice results in melting of some ice and temperature decreases. The melting of ice and dissolution of salt both are endothermic processes, and hence the temperature of the mixture is lowered up to a temperature when the solution becomes saturated with respect to both salt and ice. So, there are some examples of freezing mixtures here. By addition of common salt to ice depresses its melting point much below 0 degree centigrade. It can decreases to minus 22 degree centigrade. Freezing mixture of ice and calcium chloride .6H2O produces temperature as low as minus 55 degree centigrade. Freezing mixture of ice and ammonium chloride produces temperature as low as minus 16 degree centigrade. By using a mixture of dry ice and ether, temperature is minus 80 degree centigrade can be obtained. And the freezing mixture is a mixture of solid carbon dioxide and ether. So, it evaporates under reduced pressure could produce a temperature as low as -100 degree centigrade. This specific freezing mixture is known as thermolear mixture. Faraday in 1823 succeeded in liquefying a number of gases such as sulfur dioxide, carbon dioxide and chlorine by this method. Because of very low critical temperatures, however, some gases like oxygen, hydrogen and nitrogen could not be liquefied by simply method of liquefaction, that is cooling. So, here is a diagram for you. This is the mixture of ice and salt. This is freezing mixture and the gas is produced here, and when it goes here, this is a V tube and gas is liquefied due to low temperature. So, this is Faraday's method of liquefaction of gases. Let us discuss the Linde's method of liquefaction of gases. Linde in 1896 liquefied air by using Joule-Thomson effect and regenerative cooling technique. So, before going into detail about this process, it is essential to understand first the Joule-Thomson effect and regenerative cooling technique. So, let us discuss what is this Joule-Thomson effect. If a gas is allowed to expand through a fine nozzle or a porous plug so that it issues from a region at a high pressure to a region of low pressure. So, there will be a fall in temperature of the gas provided the initial temperature of the gas should be sufficiently low. This phenomena is known as Joule-Thomson effect. The reason of cooling is that when the gas expands from a region of high pressure to a region of low pressure, the molecules fall apart from each other. So, therefore, work has to be done in overcoming the forces of attraction between the molecules. This is done at the cost of kinetic energy of the gas as the system is thermally insulated. Consequently, the kinetic energy decreases and cooling takes place. Let us discuss what is inversion temperature. If a gas is allowed to expand under Joule-Thomson effect, for each gas there is a temperature below which the gas experiences cooling and above which it experiences heating. This temperature is known as inversion temperature and the symbol for this is Ti. The relation between inversion temperature and van der Waals constant is Ti is equal to A by Rb, or you can write it as 27 by 4 Tc. Tc is the critical temperature here. For most of the gases, the inversion temperature lie well within the range of ordinary temperature. Hence, these gases experience cooling on expansion under Joule-Thomson effect. Hydrogen and helium have very low inversion temperature, that is 193 Kelvin, it is -80 degree centigrade, and 33 Kelvin for helium, that is -240 degree centigrade. So, hence at room temperature these gases show heating under Joule-Thomson effect, but if the gases are cooled to their inversion temperature, these gases also experiences cooling. Let us discuss the Linde's process of liquefaction. In Linde's process of liquefaction, the pure and dry gas is compressed to about 200 atmosphere pressure and cooled by passing through a pipe cooled by a refrigerating liquid. Now, this cooled and compressed air passes through a spiral tube with the jet at lower end and escapes, though the jet resulting a considerable drop of temperature by Joule-Thomson effect. This cooled air passes up, cooling the downcoming air in the spiral, which is further cooled by expansion. The upcoming air is again compressed and recirculated till it get liquefied. Here you can see by this flow chart, pure dry air gas is compressed to 200 atmosphere, then it is passed through the cooling unit for cooling. Now, this cooled and compressed air is passed through a spiral tube, and at the end of the spiral tube there is a jet, due to which free expansion at the end takes place. So, finally, when the gas expands, the gas cools and liquefied. So, this is Linde's process of liquefaction. Here is a figure for you. As you can see that this is pure dry air inlet, this unit is compressor, this compressed air is passed through refrigerating liquid. So, this is cooling unit here. When this compressed and cooled air is passed through this spiral tube, this is spiral tube, and this chamber is known as expansion chamber. As you can see, at the end of this spiral tube there is a valve that is known as expansion valve. So, when the gas comes from this spiral tube and expands here, so gas liquefied. So, this is for liquefied air. Now, let us discuss the Claudius process of liquefaction. This method is based on the adiabatic expansion of the compressed gas, but it involves the mechanical work also. The Claudius method is more efficient than Linde's process. The gas is subjected to Joule-Thomson expansion, is also made to do mechanical work by driving a piston. So, the energy for it comes from the kinetic energy of the gas, which gets cools thereby. So, in this process the gas is cooled not only by the overcoming the intermolecular forces, but also by performing some external work. So, cooling produced is hence greater. In Claudius process of liquefaction, pure dry gas is compressed to about 200 atmosphere and it is cooled by passing through a heat exchanger and then led into the chamber. When it expands and does some external work, it cools to a lower temperature as result of this work, which is known as Joule-Thomson effect, a part of which escapes from the jet after passing through the spiral and cools by Joule-Thomson expansion. So, this cooled air passes up, cooling the downcoming air in the spiral and heat exchanger. The gas escaping liquefaction goes back to the compressor and the whole process is repeated over and over again until air is cooled to its liquefaction. Here is a flow chart for you. In Claudius process of liquefaction, pure dry gas is compressed and cooled. Then this gas is passed through a T tube which bifurcates. One of the tube goes to the piston for external work where it gets cooled, and one of them goes to the expansion chamber. As I told you before, there will be a spiral tube which opens at the end and where the gas expands. So, finally, the gas cools and liquefied. So, this process is Claudius process of liquefaction. Here is a diagram of Claudius process of liquefaction. The pure dry gas passed through compressor, then through cooling unit. So, the dry air gas compressed and cooled through units and then it goes here, it bifurcates. As the tube bifurcates here, you can see here one of the tube is going for mechanical work. Here is the piston and gas will do some mechanical work here, it will gets cool, and this tube is spiral tube as we have seen in Linde's process, and at the end of this there is expansion valve. So, gas will be cooled here through expansion and through mechanical work. So, this process is known as Claudius process of liquefaction. Now, let us discuss the applications of gas laws in daily life. So, first we will discuss the effect of pressure with altitude. We will discuss deep diving in sea and then aeroplane journey. Normally, we inhale about 0.02 mole of oxygen with each breath, and the partial pressure of oxygen maintains our hemoglobin about 97% saturated with oxygen. So, it allows normal metabolic process to occur. But the situation changes if we subject it to pressure changes, like we will discuss the deep diving in sea, and after that we will also discuss aeroplane journey. So, what happens in deep diving in sea? Pressure increases as we move down in sea. A scuba diver at a depth of 100 feet in deep water experiences about 3 atmospheric pressure extra, whereas at a depth of 300 feet he experiences about 10 atmospheric pressure extra. So, what happens? This increases pressure and thereby increase the partial pressure of oxygen. It affects the air canal and squeezes the lungs. So, therefore, oxygen must be diluted by another gas in the depth like helium. Now, let us discuss aeroplane journey. When an aeroplane starts to rise, it goes from an area of high pressure to an area of low pressure. At a height of 10,000 feet, a person inside receives only 2/3 of the normal oxygen he needs. So, to overcome this problem, either he breathes more deeply or more often. So, in that his heart pumps more vigorously to deliver the normal oxygen supply. But if he exercises beyond the point at which his lungs and heart can maintain the normal oxygen flow, he experiences altitude sickness like nausea and dizziness. Now, let us discuss one more application of gas laws in daily life, that is soda chemistry. In soda water bottle, carbon dioxide is dissolved in water at 2 to 3 atmospheric pressure. As the seal is broken, the partial pressure in the bottle falls immediately to 1 atmosphere, and as a result, rapid expansion of carbon dioxide causes rapid cooling of gaseous mixtures. So, therefore, fine white bubbles appear at the mouth of the bottle. One more application of gas laws in daily life, that is increase in size of weather balloon. As the balloon ascends up, the atmospheric pressure around it decreases. So, consequently, the balloon expands to a high volume so that the pressure inside equals the outside atmospheric pressure. So, viewers, in this lecture series of gaseous state, we have discussed the liquefaction of gases, the methods of liquefaction of gases, how gases liquefy by cooling, and Linde's method and Claudius process of liquefaction, and after that we also discussed the applications of gas laws in daily life. Thank you.